The last part of our stellar evolution story is what happens to the very large stars. So to give you some frame of reference, these are the stars that are big enough that while they're on their main sequence stage, so while they reach and they get that first bit of fusion, fusing hydrogen into helium in their core, they have enough mass to generate enough energy to be up here on the scale of temperature and brightness. So they are the hottest, biggest, and the brightest stars. Their evolution is drastically different because unlike low mass stars where they may or may not get hot enough to do certain things, these stars have enough mass to generate enough gravity to generate enough energy to do most of the things that we're going to talk about. So just to remind you, we're starting back from the beginning. High mass stars start in very similar ways. All stars start as a dark nebula. The dark nebula, something causes the dark nebula to collapse. A dark nebula collapses and it begins accretion, and when it's high enough to glow, we call it a protostar. It reaches a pre-main sequence star when accretion slows, and eventually it gets hot enough that in the core it can fuse hydrogen into helium. Hopefully you remember that smaller stars, once they're converting hydrogen into helium, hit a bit of a snag in that their cores run out of hydrogen. They've turned it all into helium, and they don't have enough energy right away to fuse helium into heavier elements. In larger stars, the story is a little bit different. So just like low mass stars, when they reach the main sequence stage, they are fusing hydrogen into helium. And just like low mass stars, as the hydrogen turns into helium, there's less nuclei in the core. The rate of fusion slows down a bit. The core contracts, and they start fusing hydrogen in the shell. The difference is, in the core and in the shell, when that happens, it's hot enough to also fuse helium into heavier elements. And so the supergiant stage, in other words the stage immediately after the main sequence, gets to the stage in which it's fusing both hydrogen and helium in the shell and in the core of the star. So hopefully you remember from the low mass star video that when helium fuses, it produces carbon and oxygen. The carbon collects, and once again we get fewer elements, so the rate of fusion slows down a bit, and the core contracts, raises the temperature to 1 billion degrees, and the core gets hot enough to fuse carbon. And that makes oxygen and neon. So we've got basically kind of an onion layered star at this point, where we've got non-fusing hydrogen on the outside, and then layers in the shell of hydrogen and helium fusing, and in the core we've got carbon fusing into oxygen and neon. Eventually carbon runs out. All of it has been converted in the core to oxygen and neon. The core contracts, and the helium that's being produced in the shell starts fusing, and we get carbon fusion in the shell. And this cycle goes on. We call it the CNO cycle, the carbon, neon, oxygen cycle. And it continues where we get core fusion, contraction, shell fusion, and we start fusing heavier and heavier elements. And so the oxygen that produces starts to fuse, the neon that was produced starts to fuse into heavier elements, the magnesium, the silicon, the sulfur, and eventually it produces iron, which cannot fuse. We'll come back to that. This cycle goes faster and faster for a number of reasons. There's lots of fusion going on. It's really, really hot, and there are fewer nuclei because remember, when we make several nuclei into a heavier one, we have fewer number of nuclei. Additionally, there's more and more gravity. It needs to support that weight, and so it's generating the energy a lot faster. We get these layers, as I mentioned, where we have layer after layer after layer of different kinds of fusion taking place. And this diagram doesn't even show the shell on the outside of this. So this makes a star that's expanding outward, and that outer envelope is much further away than it was before because of all this fusion pushing the surface away. So we have a red supergiant at this stage. Just to give you an idea of what we're talking about, remember, we're fusing several nuclei into heavier nuclei. So we got our carbon fusing into oxygen, and oxygen and helium making neon, and so forth, and we're getting larger and larger elements, eventually producing this nucleus of iron. I mentioned before that heavier elements fuse into heavier elements, which fuse into heavier elements, ultimately producing iron in the core, and that iron can't fuse. And so because iron doesn't fuse, all of a sudden we get this element at the center, where, remember, the center is where all of the gravity from the rest of this super humongous star is focused, and all of a sudden at that outer center, it's like playing a game of tug of rope. And if you're watching and both sides are pulling as hard as they can, and then suddenly one side lets go and the other side falls down. It's kind of the same idea that we have this tug of war between gravity and outward pressure due to fusion, and at the core, it lets go because there's no more fusion. And the core collapses. This happens in less than a second, a fraction of a second. It's insanely, it's in my mind, I can't even conceive of this humongous star doing something that big, because it would be faster than any speed that we're have an understanding of as human beings. And during that time, during that collapse, there are all kinds of nuclear fusion. So it's not a specific order to where helium fuses to make oxygen and carbon. It's helium fuses with silicon and neon and all kinds of random things get kind of smushed together. All these nuclear reactions are happening, and that's when all of the rest of the elements in the periodic table get made. And so every element that's made up, that makes you up, that makes up the Earth, all of those other exotic elements happen during that momentary collapse of a star. And so remember, hydrogen and helium are the most abundant materials in the universe. And all of the other ones that we have come from stars, and specifically the most variety of them come during this moment of collapse that we call a supernova. Momentarily, that produces a ridiculously huge amount of energy, and those collisions produce a shock wave. It's kind of like if you've ever seen someone walk into a wall and they kind of bounce off. I like Funniest Home Videos. So when you see that and they kind of bounce back, that is the supernova. The collision, and they call it shell rebound. Everything collapses in on that core. We have all those exotic nuclear reactions, and the supernova is that outward expansion. After supernova, there's two things that remain. There is the center. The center either becomes a neutron star or a black hole, depending upon the mass of the star. And then the stuff that expanded outward becomes the supernova remnant. It's basically a fading cloud, and that fading cloud is fading because the material keeps getting thrown outward and outward and outward. And so the supernova remnant doesn't last very long. There was a famous supernova that happened in the constellation Cassiopeia in the 1500s. And during that time, the supernova remnant was visible during the daytime. It caused all kinds of discussions about whether the heavens were changeable or not. And a guy by the name of Tycho Brahe helped us figure out that was really far away. It wasn't just in our sky. I digress. Anyway, that supernova could be seen during the daytime. It was so bright. We, of course, can't see the supernova remnant now during the daytime. And that's because the gas is dissipated. We can see it with a telescope, but it's no longer nearly as bright as it was. These are all examples of supernova remnants that we've observed from our Hubble telescope and others. I should point out that there are different types of supernova. I'm not going to get into it now. It's not something we need to worry about. But do keep in mind that what we're talking about is one type of supernova. So what happens to the core, the dense stuff that collapsed that didn't rebound? And so there are two possibilities, and the two possibilities depend upon the mass. So the stars that are super big enough to supernova, but are on the smaller side of that, and they collapse into something kind of like a white dwarf, only we call it a neutron star. It's much denser than a white dwarf. All of the mass of the sun is swished into a size of something smaller than Cedarburg. And 1 teaspoon would weigh 100 million tons. So we're talking crazy dense. And at this extreme density, the degeneracy pressure that holds up white dwarfs, in other words, that prevents them from collapsing, is easily overcome. So the electrons can be smushed together closer. What keeps neutron stars from collapsing is that the protons and the electrons that are there actually combine to form neutrons. Hence the name neutron stars. What's really cool is a lot of them spin really fast, and they are crazy hot. A lot of them have really, really strong magnetic fields, and what's really cool is that if they're spinning, we can detect these magnetic fields that kind of show up as a blinking light. We call it a pulsar. So pulsars give off radio signals, and as they spin, the pulsar, when it spins towards us, we can detect that radio signal, and then as it spins away on this side, we can't. And so the radio signal seems to pulse. Kind of like a lighthouse, as you would see the light blinking from far away as it spun towards you, away from you. If a neutron star isn't spinning, isn't a pulsar, it's probably isolated all by itself, whereas if it's spinning, it may be in a binary system or have a planetary system around it. Finally, for those really, really big, gigantic stars, they're just absolutely mammoth. And they are the end state of a star in which there is so much gravity because there's so much mass that they collapse in on themselves. And there's not even light can escape it, which is why they're black. And it forms from stars, again, whose mass is just so large that not even the production of those neutrons that I mentioned can hold it up. So it's way, way more massive than dwarf stars or neutron stars, and it collapses to a radius of 0, which for a lot of people is really hard to imagine how you get all that stuff into a radius of nothing. So it's still really hard for us to picture, but it's a radius of 0 with infinite density and gravity. So because of that, people have this misconception that if you were to somehow get close enough to one, you'd get like sucked up, like you were being pulled down the drain. And that's a little bit true and a little bit not. It has a lot of gravity, but just like that star, the star has a point where you would be sucked in if you got too close. Earth has a point like that too, where if an object, like a satellite, man-made or otherwise, or a meteoroid gets close enough, it will come under the influence of Earth's gravity and it may come and hit us. So that's how gravity works. There's a distance from which, if you're close enough to the thing that's massive, its gravity will pull you in. And so black holes have that distance too. And so unless you're within that distance, you're not going to get sucked in. So the suck-in light distance for light is called the event horizon. It's the boundary of the black hole where light can eventually get out. The size of the black hole, in other words, the size of the event horizon, which is a radius, it looks like a circle, is proportional to its mass. So the larger the black hole, the larger the event horizon would be. There are different kinds of black holes. Some black holes are not the result of star collapse. Those black holes would be the ones that are at the center of galaxies. We're pretty sure that our Milky Way has a black hole at the center of it. And those would be way bigger than one that happened because of a supernova. And again, the gravity nearby, not inside, because that's a whole different ball of wax, but the gravity nearby is strong, but still not enough to pull you in unless you are in the distance that it would have been if it was just for that star. And there's all kinds of crazy complicated math by very famous scientists like Einstein and Hawking to back up the existence of black hole. And again, within the last 5 years, we've had some observational evidence of them as well. Finally, the supernova can eventually lead to, number one, the expanding gas from it can expand to become interstellar medium, and number two, the force of the explosion can be the causal event of a different dark nebula collapsing and eventually leading to a star. Just as we talk about the HR diagram, if you recall, smaller stars all stars start over here on the HR diagram, and as they reach main sequence, where they are on here depends upon their size. And a star the size of our sun will go red giant, yellow giant, AGB or second red giant, and then fizzle out as a white dwarf. Stars that we've been talking about today start the main sequence on this end, and then as they burn heavier and heavier elements and contract and expand during those last couple hundred years when they're making different things, different elements, they'll go back and forth like this until they eventually supernova. And after that, we don't track them on the HR diagram. Okay, if we put it all together, today's discussion, we started with main sequence. The main sequence stars eventually become a red supergiant, where they have layer after layer after layer, fusing different elements, surrounded by that outer envelope of hydrogen. When they produce iron in their core, fusion in the core stops, it contracts, and the rebound is the supernova. What happens of the remnant of the supernova? We have the gas cloud that eventually dissipates, and then we have a neutron star for the large but not as massive high mass stars, and a black hole for those stars that are super humongous. That's it for our discussion on stellar life. Please make sure you contact me if you have any questions. Remember, I'm just looking for you to get the basics.